Hi, this is Jeff Blair of ISA St. Louis section. Today I'll be talking about radar for solids and powders. Full-time, I'm the offer manager for level at Schneider Electric. I'm an ISA senior member assigned here to the St. Louis section. Before we start, I want to thank you for your investment of time today, and I encourage you to work with your favorite vendor and their technical support to help select a radar. I have to give the disclaimer that you'll see I may favor a particular type of radar for solids level applications, but there is no one-size-fits-all. Please work with your qualified personnel or technical support to pick a model. And if you haven't seen my video on a beam angle overview, you can check that out at the link here. That pertains a lot to what we'll talk about today in terms of radar for solids and powders. You'll have to forgive my crude artwork, but this demonstrates some of the existing technologies that are very popular for solids level and powders level. You'll see level switches here in the side. They either sense level or they don't, like this one would be tripped for sensing level. This one doesn't see anything yet. Ultrasonics, which use sound waves or acoustic waves, there's several of these installed in solids level applications. And then the good old reliable mechanical methods where a person stands on top of the vessel and drops a rope or a plumb bob down to check the level. There's nothing wrong with any of these methods, and actually they've probably advanced in recent years and gotten a little bit better. But it seems like when you watch vendors, when you watch market data and things like that and applications, you see radar is continuously growing in popularity not only for liquids but for solids as well. So this gives just a general view of typical radar you may see for solids level applications. 80 gigahertz radar with a very high frequency and a narrow wavelength, small wavelength. 24 gigahertz, which are often good for larger particles. And guided wave radar, very reliable, but it is a contacting technology with a rope or a rod that actually sticks down into the process. Let's look at the 80 gigahertz radar first. It's the most universal of the two radars. We're looking at the two free space radars today. Well, why is that? It has an 80 gigahertz frequency with a small wavelength that can measure any size medium. The 80 gigahertz specializes in small particles like fine powders, but it can handle the bigger stuff too. It provides an increased focus. This narrow beam gives you an increased focus. This results in better dynamic range, better reflection, and a good ability to work with dust. And if you've got a high nozzle, that narrow beam can fit down through the high nozzle to still give you a good level measurement or distance. The 24 gigahertz is certainly still applicable. It's got a larger wavelength that works better with bigger particle dimensions like rocks and granulates. And you'll notice that beam is just a little bit longer. Here we've got a 9-degree beam with a 3-inch drop antenna. This one, by contrast, the 80 gigahertz is a 2 3/4-inch lens antenna with a 4-degree beam. So this 9-degree beam is going to be a little bit bigger, spread its energy out just a little bit more than the 80 gigahertz. Choosing an antenna for any radar is probably the most critical part. With the 24 gigahertz radars, you'll often see things like drop antennas or horn antennas. And with the 80 gigahertz, you'll see a smooth peak antenna. So there's very little, almost no protrusion into the process at all with an 80 gigahertz antenna versus a 24 gigahertz has a horn or a drop antenna that comes down inside that nozzle or inside the tank. So we've looked at the 24 gigahertz and 80 gigahertz free space radars for solids. Why would you consider an 80 gigahertz? And again, it goes back to that smaller beam. The smaller beam gives a better reflection off of solid surfaces. This translates into a more reliable signal. More energy down, more energy concentrated in one area, the more energy you're going to get back as a return signal or an echo. And if you want to even look outside the process industries, you can look at the automotive industry. Automotive industry is predominantly choosing 80 gigahertz or high frequency radars over 24 gigahertz. If you look this up on Google, you'll see quite a few articles and white papers and things on that. But why are they doing that? Simply, the higher frequency gives better accuracy and better resolution. And I think of it as kind of the evolution of the auto industry. And you've got we all remember leaded gasoline and carburetors, and now we have unleaded gasoline and fuel injection. And the same applies to radar. We went from 24 gigahertz, and now we're moving on to 80 gigahertz. And think about what that radar in your car, if you've got a car with a radar, it's probably sitting right behind the front emblem in the grille. What is it measuring? It's not like we're doing liquid levels where we've got a 20-foot tank of water or something in front of us we're trying to take the level for while we're driving our car. It's solids. It's that radar is aiming in front of it. It's going to see the back of a semi-trailer. It's going to see the plastic bumper of the car in front of you. So that 80 gigahertz radar that's in your car is measuring solids as well. And think about how accurate and reliable those are when working in a car. So we talked about the challenges of solids, low dielectrics, emptying, filling, uneven surfaces, and things like that. What do we need to do to ensure we're giving our radar the best chance at success? And the next step is, what are we going to do to properly install the radar? I'll show you a few accessories that may be helpful to your solids level radar in just a minute. First, let's go back to our 80 gigahertz example. In a solids level application, a rule of thumb is that whatever your beam sees is averaged out by the radar processing algorithms and software. Because there are almost no even surfaces in solids level measurement. If your client would like to average somewhere outside the normal beam angle, you can do that for them. The photos on the left here and the middle show what happens when we install the radar flat, just sit it on top of the nozzle or the flange here, and it shoots straight down, versus this drawing on the right shows us if we actually angle the radar to shoot that beam somewhere outside it normally would if it sat flat on top of the tank. You don't have to aim the radar at any particular point, but remember, the radar is going to give a level based on what it sees. So if you look at our installation here, let's assume that this 80 gigahertz radar is shooting its beam straight down, and where that red dot is, where it intersects the level, that's what it's going to see. The yellow oval represents the 24 gigahertz. So if your customer says, hey, that's fine, I'm okay with the level being at that point, but chances are they're going to want to try and hit what's called this angle of repose and hit it in the middle. So half of the level is above the angle of repose, half the level is below it. So you may want to try and hit it there, and that's where these accessories will come into play. One word about this. This is an advantage of the 24 gigahertz radar. If you look at the yellow oval, that is a representation of the wave beam size of the 24 gigahertz, and you'll notice it's bigger than the 80. Remember, we talked about how the radar tries to average out what it sees in a solids level application. Well, that yellow oval is going to give us a better sample size to average out. It's a little bigger. The drawback is we won't have as reliable of a signal because the wave beam is bigger, it's spreading its energy out, it's maybe a little harder for that reflection or echo to get back to the radar. So if you've decided you do want to angle that radar, there's accessories you can use, such as universal flanges or orientation systems. And then there are also slanted flanges. This happens to be a 2-degree slanted flange. But remember, you don't have to tilt the radar at the angle of repose. Ask your customer, do you want it to see the radar to see below it, directly below what it is, or do you want to try and aim at that angle of repose? So think about that. And if you do want to try something a little bit outside of the box, you can install more than one radar to get a profile of the solids level. Generally, most modern radars work pretty well with dust. They have things like high-pass filters to remove errant dust signals that may be close to the antenna. And we know working with solids and powders, they're often very, very dusty environments. If you decide the environment is dirty and material may clump or stick to the antenna, be it a horn, or a lens antenna, you can use a purging accessory, which is often air, to, at certain intervals, blow the material off of the lens or off of the antenna. So before we depart, I want to go back and talk about algorithms. If you've watched this, you might be thinking, okay, I've used liquids level radar before. Maybe you've even used an 80 gigahertz liquid level radar. What's the difference between a liquids and a solids level radar? They both measure level. Maybe they have some slight cosmetic differences, but they're very similar, except how they process their signals. Each radar has specific algorithms that make it specific to use in liquids or solids. So when we work with a liquid level measurement, usually a reliable measurement can be had with one single pass. But when we work with solids, that's not always the case. Remember, the reflections are often weaker. We can get some erratic signals mixed up in the echoes that come back because of these different profiles. So what the algorithms do is they overlap several measurements to determine which signal is the true level. Remember, we talked about that averaging. That's what a solids level radar is going to do. Finally, I'd be remiss if I didn't mention how solids are normally measured. It might be level, it might be distance, but often it's volume or mass. And with most radars, you can build a strapping table with at least 2 points using the keypads or connecting it to Pactware or something similar to that to build a strapping table to get volume and mass measurements out of your tank or your vessel. In closing, I want to say thank you very much for watching, and I'll leave you just with this brief parting shot. We talked about 80 gigahertz radar for solids and powders and 24 gigahertz radar. Overall, an 80 gigahertz gives a focused, more reliable signal, but the 24 gigahertz has an advantage where it's got a wider beam that's good for a nice average of the solids level profile. So thanks for watching this ISA St. Louis video. I do appreciate your time and attention and hope to talk to you again. Thank you very much.